Hi and welcome to video 7 on this video series from Unit 4 Topic 2 Specialist Mathematics, and in this video we're looking at some further examples of Newton's law of cooling, which is a specific case of differential equations. So let's have a look at these examples now, starting with example 4 from my OneNote. And in this example we're talking about coffee cooling, and it's a fairly routine example. The rate at which a hot object cools, is approximately proportional to the difference between its temperature and the temperature of the surroundings. A cup of black coffee is made with boiling water, so therefore we assume it starts at 100 degrees, and I know that that is scientifically not necessarily possible, but we're going to work with that assumption. After 2 minutes, it's dropped to 80 degrees, and the room is 25 degrees Celsius. Use a differential equation to find how much longer it will take to drop to 50 degrees Celsius. So, we start by defining capital T as our temperature of coffee, and this is in degrees Celsius, and little t as time, and we're given our first time in minutes, so we say in minutes. That's pretty badly drawn minutes there, but that'll work. And now we go through and set up our differential equation and solve it. So we know that dt, d little t, is proportional to, and this is a Newton's law of cooling, so T minus 25, which is the room temperature. That's where it's heading. So it's proportional to the difference, as we're told in the question. And therefore, dt, d little t, is equal to kt minus 25. And now we can solve our differential equation. So we get dt over t minus 25 is equal to k dt, and you've seen this in the last example. We integrate both sides, and it gives us the natural log of capital T minus 25 is equal to kt plus some constant. So now rearranging, as you've seen, we get t minus 25 is equal to a e to the kt. So I've skipped that whole e to the kt plus c and gone straight to the a version, and therefore capital T is equal to a e to the kt plus 25. So my temperature in terms of time is there, but of course I'm dealing with two unknowns, which is pretty standard. Now, going back up, I know that the initial temperature is 100 degrees, that's my assumption, and T2 is 80 degrees. So T0 equals 100 degrees Celsius. So I put in my 100 degrees, that's 1,000, equals a e to the 0 plus 25, and I get 75 is equal to a. And therefore T now equals 75 e to the kt plus 25. And I know that T2 is equal to 80 degrees. And so I can put that in as well. I get 80 is equal to 75 e to the kt plus 25, which gives me 55 equals 75 e to the kt. Divide by 75, take a log of both sides, I get kt equals the natural log of 55 over 75. Now 55 over 75 is 11/15, and so my t of course was 2, so I get k is equal to a half log 11/15, and I'm going to maintain that value. I'll just write about this t and put a 2 there just so that you see that substitution. I probably should have done a bit earlier. So that's my k value, and my a value is 75, and so I've now got t is equal to 75e to the half log 11 over 15t plus 25, and I want to know when does temperature equal 50, and so now I just put in 50 and I solve. 75e to the 1/2 log 11 over 15, I'm missing an one there, t plus 25. I subtract 25, divide by 75, and I get e to the 1/2 log 11 over 15 t equals 25 over 75, because I've subtracted 25 from 50 as 25, which is 1/3. So I get a half log 11/15 t equals log of 1/3, and then I get t equals log of 1/3 divided by a half log 11/15, and of course obviously That's equal to about 7.09 minutes. And I've rounded that pretty dramatically, but 2 decimal places right at the end is fairly appropriate. And just be careful now, it's not asking for minutes, seconds, it's not asking for it in hours, or it's not asking it for it beyond a certain time so that you've finished the question. And I should probably check that. And how much longer? So the how much longer here kind of implies maybe that the answer is therefore 5.09 minutes after 80 degrees Celsius. So just be careful with how the question reads. Okay, let's look at a second example, example 5, and this one's a little bit trickier because it involves 2 cups of coffees and transferring some information across. So 2 cups of coffee are made at the same time with boiling water. So again, we've got T0 equals 100. Milk is immediately added to 1 cup, but the other is left black. When milk is added, the temperature drops by 10 degrees, and it drops another 10 degrees in the next 2 minutes. So I've actually got T0 equals 90 for cup 2, and T2 equals 80 for cup 2. Assuming both cups of coffee have the same characteristics for cooling, find the... Now, I'll just make a note of that. The same characteristics for cooling, and that means that K is equivalent. That's what that's saying. Same characteristics for cooling. Find the temperatures of both 5 minutes after they've made, given that the room is 25 degrees Celsius. So there's our room temperature. Can you refine your model to take account for the fact that different people add different amounts of milk? Now, I'll probably leave this one off, but that's a nice little one to play with if you want to take your understanding a bit further. So let's have a look. We're dealing with cup number 1 to start with, and that's the milk cup, because we have a lot more information about the milk cup. So we get this, dt, d little t, is proportional to t minus 25, and we know that T0 equals 90 and T2 equals 80. So I'm going to leave it as those values and deal with that, but I just want you to keep in mind that I haven't defined variables here or really set this up fully appropriately, but I'm assuming you kind of know how to do that now. So I get dt equals kt minus 25, which leads to the integral of dt over t minus 25 dt equals the integral of k d little t, and that gives me log t minus 25 equals kt plus some constant, which gives me t equals a e to the kt plus 25. Now, T0 equals 90, that will lead to A is equal to 90 minus 25, which is 55. So I'm just going to jump straight to that. Is it 60? That's completely wrong. Let's go with 65. That's much better. So T is equal to 65. If you put in T equals 0 and 90 degrees for my capital T, you'll get 65. E to the KT plus 25. And we also know that T2 is equal to 80. So therefore I get this. 80 equals 65e to the 2k plus 25. Subtract 25, divide by 65, and I get 55 over 65 equals e to the 2k. Take a log of both sides, divide by 2, and I get k is equal to a half log. And 55 over 65 is 11 over 13, by the way. And that's my k value. Now this is going to transcend across into the other cup because we've got the same cooling characteristics. So that rate of cooling comes from the k value. So I'll be using that. But the question does ask me to find the temperatures of both 5 minutes after they've made. So I've got model 1, which is the milk model, is this. T is equal, I might even call that T1, is equal to 65e to the half log 11 over 13 plus 25. And then I've got model 2, which is the black coffee. And T2 equals, now I'll have to find the A value again in model 2 because I don't know it, but I do know that the A value is always that difference, the initial difference. So that will be 75 E and the same characteristics of cooling, so half log 11 over 13 plus 25. So you can go through and find the A value, but the black coffee starts at 100 degrees. So 75 plus 25 is 100, and that's a slight difference to the model there. And I want to find, oh, there should be a little t here, and a little t there, sorry. At t equals 5, I get the temperature is equal to 65 e to the half log 11 over 13 times 5 plus 25, and I get the same thing in model 2, but this time I've just got a 75 at the start. And so the first one gives me 67.81 degrees Celsius, so I'm just rounding to 2 decimal places, but I've used exact values the whole way through. And the second one gives me 74.39. And again, or actually 74.40 round up, and that's degrees Celsius. And again, keeping the exact values the whole way through. And so the question asks, blah, 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 blah. Find the temperatures of both 5 minutes after they've made, given that the room temperature is this. So I've found the temperatures of both. Now, can you refine your model to take into account the fact that different people add different amounts of milk? Well, we dealt with the milk quite nicely by recognising that it dropped 10 degrees Celsius based on that particular set of milk. If we double the milk, does it decrease by 20 degrees? You'd need to have a little bit more information about how adding, say, milk from the fridge, which we assume to be 4 degrees, how mixing 4 degree temperature liquid with 100 degree temperature liquid affects the temperature of the liquid. And if we assume that it's a straight linear ratio, well, maybe we could actually work out what percentage of milk was added to 100% coffee, if we call it 100%.